yesterday we started this topic which is about travel time studies. Another name for it is journey time surveys. Okay, you can find out the delay using these studies as well, and these are some of the uses of a travel time study. Okay, what we also talked about was the different methods of doing travel time studies. What are the methods? Test car, okay. License plate. Vintage point, observation from a vintage point. And you can take a video, okay, which works with the other methods. And yeah, you can put some tracking devices in the car so that you don't have to take the measurements manually. Okay, so okay, this is a table which is showing the sample of a travel time study. Okay, so on top of the table you see some general information, okay, like the name of the highway, the person with the observation, date, time, and the starting location. Okay. Now what you see in the first column of the table are different points which they have marked for taking the observation of travel time. So the first observation of travel time will be taken at MP16. MP stands for milepost. You can see it's written on the top. So the first observation of travel time will be taken on MP16, the next one on MP17 and 18 and so on. Okay. So these are the points at which you will note down the observations. Okay. Next column you have the distance, and the distance is cumulative. Okay. So all these values are from which point? Milepost 15, the start location. Look at the top. Okay. So all the cumulative distances are from there. Similarly, in the third column, you see cumulative travel time. Again, all of it from the start location. Okay. And you can see it's given in minutes and seconds. Okay. So this means the first value means 1 minute 35 seconds. Okay. Second one is 3 minutes 5 seconds. Okay. Why are we writing it like this? Why not just seconds or just minutes? Why are we writing it like this? So what? Can it ever travel? Can be in seconds only? So instead of writing 1 minute and 35 seconds, you can write 1.5 something. Start and point? No. It's because of the stopwatch. They are using a stopwatch. Okay. So a stopwatch will show the time like this. It will finish the minutes and then it will show the seconds. If it goes into hours, then it will show hours, minutes, and seconds. So whatever you have to do with the values, you will do it later on. This is as you saw in the stopwatch. Okay. So whenever you are taking observations, we write it as it is. Whatever conversion you have to do, we'll do it afterwards. Clear? Okay. It's more convenient. Then the next 4 columns, you can see they are per section. Per section means each value is between 2 points, not from the start location. Each value is between the 2 points next to each other. Okay. So for example, you see the third value. Okay, the delay column. So this column is stop delay. So for how much time the car was stopped. Okay. So the third value shows 42.6 seconds. So the car was stopped for 42.6 seconds. Where? Between what? Which points?
18 and 17.
17 and 18. Okay. The next one is between 18 and 19. Clear? Okay. And then they are also showing for how many times the car was stopped. Okay. So again you see the third value is 3. Okay. So maybe the car was stopped at different points for different durations. At first point maybe stopped for 10 seconds. Next point stop for 15 seconds or something. Okay, so this is the total number of stops. So you may have more than one stop, and this is the total time of stopping. Clear? And this is the travel time of the section between 2 points. Okay, so if you look at the second value, how do I got this? How do I get this? 1 minute 30 seconds. We calculated it, but how? Minus what? Again, like we did for the z table, the z probability of the z, you take the difference of the two cumulative values. Okay, so 3 minutes 5 seconds minus 1 minute 35 seconds will give you 1 minute 30 seconds. Clear? Okay. This one was from the starting point, this one also from the starting point. You take the difference, you get the time between them. Okay. Okay. And since you are inside the car, then you know the reasons as well. You are looking at the stop delay, right? So you know the reasons as well why the car was stopped. Okay. So you can see it can be a signal, it can be a double parked car. We don't do it, right? And it can be because of a school bus and so on.
Which is mean 305, which is equal 135 plus 133.
Huh?
305,
Yeah.
which is equal to 1.
This process, yes. Clear? Okay. This is another example of a journey time survey from Bahrain. Okay, I got it from a company. So again, you see some basic information on the top, which route they are covering, what's the name of the highway. They didn't write the person who is doing it, but you can see the day and time and date. Okay, and if you are doing more than one trial, okay, then you have the trial number as well. Again, you can see the start point, the intermediate points. Okay, these are the intermediate points, and then you can see the end point. Distance is cumulative, so everything from the start point. Okay, and then you see the time. Okay, now which time is it? Huh? Which time is it? They reach where? The point. Okay, but again, from where did they get this time? From the stopwatch? Stopwatch? From the clock. You can see it's 2 p.m. Okay, so instead of using the stopwatch, they're using the normal watch. Okay, and obviously, then in the end, you will do the difference. Okay, and then you can see the reasons again for delay. There was a delay. What was the reason? Clear? Okay, so the data is the same, the method of observation can be different. Okay, let's say we have an arterial which has a true mean running time of 196 seconds. It's a 3-mile section, and the standard deviation of this time is 15 seconds. Okay, so mean is given, standard deviation is given. Okay, what are they asking for? Let's assume that this time, running time data also follows normal distribution. Okay, so if it is normal distribution, then we can apply which theorem? Central limit theorem. Okay, so central limit theorem can apply to it because it's normal distribution. What are they asking for? Find out average and 95% confidence interval of speeds. Okay, they want the average and the 95% confidence interval. Clear? Okay. Now, first of all, you can see, before we start any calculation, keep in mind, in this whole topic of travel time studies, we will not use any new equation. The data will be different, some of the concepts will be new, but as far as the calculations and equations are concerned, all of them are same as what we have used in the spot speed case. Clear? Okay, so they are asking for average speed and 95% confidence interval of speed. So first of all, how do I find out the average speed? distance over time. Okay, do I have time? 196. And do I have distance? 3 miles. Okay, it's given. So, and since it's in miles, so it's better to keep the time in hours as well. Okay, so it will be 3 upon 196. Okay. How much? $55. Okay, the next thing is the confidence interval of the speed. Again, we'll do the same thing, right? We'll do distance upon time. So then I need the confidence interval of time. Okay, to get the confidence interval of a speed using distance upon time, I need the confidence interval of time. You cannot do confidence interval with distance, right? Distance is fixed. Okay, so according to central limit theorem, the 95% confidence interval is mean plus minus 1.96 E, where E is S upon root of n. Okay, so can we get E? Yes, can I get E? What do I need? N? Do we have N? We have? Running time is time. What is N? Number of observations. Okay. So we don't have N. So like I mentioned, we are still using the same equations, but there are some new concepts which you need to learn. So look at the question. Second line. What time is given? 196 is what time? Which time? Which mean? True mean. And after mean it was written? Running time. Okay, now understand both terms. Running time means it does not include the stopping time. Running time is without a stopping time. Okay, first thing. Okay, running time means without stop delay. Secondly, so I need E here. Okay, in the question they are saying this is true mean. So whenever the term true is used with any value, it means for the entire population. Okay, it is already for the entire population. In that case, E can be taken same as standard deviation. Okay, if the mean is given for the entire population, or they write it is the true mean, then we don't need to calculate E. Whatever standard deviation given is E. Clear? Okay. So here we will take E equals to what? How much? 15. Why? Because true mean. Got it? You see, look at the question. Okay. So now you can calculate the confidence interval directly. You know the mean, you know the E value. Okay, so give me the confidence interval.
One into one.
1.96, yeah.
Equal.
E forward.
One six six.
And
2 to 1.
2 to 5.4.
4.
Okay, now like we calculated the average speed, you can calculate the confidence interval of speed as well. Okay, you will use these 2 times. How much is it? And 47 point. Any questions? Clear?
We have the two mean, why are we calculating standard deviations and confidence interval?
True mean can also have confidence interval. What's the problem with that? Mean is still one value, right? Mean is still one value. It's not the entire data. The word true means that it is truly the mean of the entire data. This is what they mean. Okay. If we just say the mean running time, that means yeah, it's a mean of a sample. But when they say the true mean, that means yeah, now you are sure that this is the center of the entire data, not a sample. Okay, but there is the data. There is a data. Okay, that's wherever there is a data, there is a confidence.
For each sample, it may be within that range, with the mean of the.
Yes, yes. Okay, this is how they explain that if you take any sample, the mean will be in this range. Clear? Okay, any other question? Okay, so this is now a travel time data given in the form of a bar diagram. Okay, instead of having a table, now we have a bar chart, a histogram. They call it a histogram. So what they are asking for is the average speed again and 95% confidence interval of speed. Okay, one more thing. This confidence interval which you calculated in the previous example, or the average speed you calculated, since we calculated it from running time, so we'll call it running speed. Got it? When you calculate the speed using running time, you'll call it the running speed. Okay? In this case, they have given us a travel time data. Okay? This graph is for the travel time. Okay? So, like we did here, if you want to calculate mean speed, you need mean time. If you want to calculate confidence interval of speed, you need confidence interval of time. Clear? Okay? And as I already mentioned, we will not use any new equation. We will use the same equations which we have used for the spot speed. So you can see this one is for the mean. Okay, so I need 3 things here: n, s, and capital N. Okay, what was n? Number of observations for each group or each value. Okay, where is it in the graph? On the y-axis. The y-axis of the graph gives you number of observations. Okay, for each bar. Each bar is a value. Okay. What was S? Huh? The value itself, because for which you have the number of observations. Okay. So in the graph, these values are on the x-axis. Okay. So you will pick S from the x-axis and you will pick N from the y-axis values. Okay. And what was capital N? No, number of all observations. So from where do I get it? Summation of groups. What groups? Summation of observations of each group. Okay. So how much is it now? In this case, what is N here for me? Why? Because? Why? You did it? Okay, it's 20? Sure, everybody? Everybody did it? Everyone did it? Okay. They didn't know you will do it, so they wrote it here. Okay, but don't worry, it will not come like this in the exam. You will do it, okay? But the point here is, okay, the point here is you have to add the y values, okay? Don't count, add, don't count. Okay, so this is one value because it's 1 plus 1 plus 1 plus 2. This is why I said don't count, add. So 1 plus 1 plus 1 plus 2 plus 5 and so on. Clear? Okay. So N is 20 here. So give me the mean now. What is the mean? Okay, now for the 95% confidence interval of speed, we are using the same equation, right? Mean plus minus 1.96 E. Should I calculate E here? Should I calculate E here? Yes? Why? Because it's not true mean and it's a sample. It's a sample. You calculated the mean, right? Can you call it true mean? Huh? Like you can, but you shouldn't. Some of you would. Right? This is a true mean. But you cannot because it's a sample. Okay? So true mean cannot be for a sample. So we will calculate the standard deviation here. And then we will calculate the E value. So the equation for standard deviation is given, same equation, using the same parameter. Give me the standard deviation. 8.56. Okay. And then the confidence interval. Two, three, 5.3.
9201.7.
Okay. Then the confidence interval for speed. Huh?
45.9.
How much length? 3 months. Now you read, huh?
Very good.
How much?
45.9.
Yes, any problem? Clear? Everything is clear? Okay. Now, what was the difference between travel time and running time? See here, in this question, we are dealing with travel time. Previous question, we are dealing with running time, right? So, what is the difference between them?
Running time without stop.
Travel time without?
Running without stop.
Running is without stopping. Okay, running time is without stopping. So if, for example, if somebody says that this one and the previous example are for the same highway. So now you know the running time. Now you know the travel time, right? You can calculate what? Delay. Okay. So delay will be simply the travel time minus running time. The mean of travel time you calculated here 218.5. The mean of running time given previous question 196. So how much is the delay? Okay, any problem? Is it clear? Yes. What happened?
Vector for the calculation of the speed, impedance level. Do we have to calculate the mean speed or
From the time.
so we don't have to calculate the mean speed?
Okay. Okay. In this, what we just did now was calculating the delay using the running time and the travel time. There's another way to calculate the delay using the chance of delay, the probability of delay. Okay. You see 3 columns here. Okay. So let's say on a highway we have 2 signals. The average stopping time on a signal is 40 seconds. Let's say average stopping time on a signal is 40 seconds. So if somebody stops at one signal, their average delay will be 40. If somebody stays at 2 signals, their average delay will be 80 seconds. Okay. Then they do another study of how many people actually stop at both signals or one signal or don't stop at all. Okay. These are the chances. Okay. You can convert them into probabilities, percentages. So 0.569 means what percent? 56.9%. Okay. So 56.9% are those who are not stopping at all. So for these 56.9% people, the delay is 0. Very good people. Driving in heaven. Then we have 30% people who are stopping in one signal. So the average delay is 40. Okay, normal people. Then 13.1% people who stop at both signals. Not good. Okay, their life is not good. So their delay is 80 seconds. Okay, so how do I calculate the overall average now? Using these numbers. I multiply the delay with its probability or chance. Okay, so the delay in this case will be 0.569 into 0 plus 0.3 into 40 plus 0.131 into 8. So the value multiplied by is probability or chance. So what do you get? How much?
22.4.
22.48. Any questions? Okay, now the last thing, because we covered in the other section as well, is again something which we did earlier for the spot speed data, which is the calculation of sample size. Calculation of number of samples. You can see the equation over there. Okay, it's the same equation. So they are asking for how many number of runs are required. Okay, if you go back to the previous example, the previous bar chart, again they were writing runs. Run means one travel time observation. A run means one travel time observation. Okay, so you don't have to run. It's just an observation. Okay, so how many runs means how many observations, how many samples. Clear? Okay. So they are saying what? Use 95% confidence interval. So this equation is for 95% confidence interval. Then use 2, 5 and 10 plus minus. These values are what? These are E values, the tolerance levels. Okay. And then use standard deviation of 5, 10 and 15. Okay. The S values. Okay. So they are looking for a table like this. Okay. So give me the values. Yes,
94, 96,
like this. 24, 96,
216.
216. Okay, next.
4,
4,
16,
16,
24, 35.
1. You're rounding it off yourself, huh? What was the value?
0.96.
Did you round off somewhere else?
Yes.
Where? Give me one example, just one. Oh, okay, what were these ones? 0.96?
Just 1 and 3.84.
3.8? And?
8.6.
Huh?
8.6.
8.64?
Yes.
Okay. Let's say if this value was 4.1, let's say, just an example, okay? If this value was 4.1, how many samples you will take? 5 or 4? 4? Why? 5 or 4?
More, we need.
Huh? Yes. This is exactly my question, huh? Okay, go.
More, we need.
We need more. Okay, more is always good. If you do less, you are doing less than required. This is a required. This is a required. You cannot do less than this. Okay, keep it in your mind. Like what we are doing now. We are doing more than required, right? Time is already up. Okay, so we cannot do less. First point. Secondly, when I increase tolerance or the error, number of values are decreasing. Because more error means less accuracy. For less accuracy, you don't need more values. Okay? When standard deviation increases, number of values are increasing. Okay? Standard deviation means variation in the data, dispersion in the data. So if the data has more variation, then I need more values to cover it. Okay? If I just take the sample from one class, I just need 2 or 3 values. If I take the sample from entire university, then I need some values from each class. Okay? To cover the whole university. So this is the same thing. Okay? Covering more S means covering more variation. Clear? Okay. Okay. Thank you.